On paper, the golden rule of ship safety and watertight integrity is simple. Keep the water out. You build a heavy steel hull, seal it tight, and the ocean stays on the outside. Simple enough, right? Now, obviously, a ship's hull isn't a perfectly seamless, solid sheet of metal. You've got openings below like sea chests, overboard discharges, and ballast suctions, all cutting through the plates. But all of these openings are tightly controlled by heavy valves. Things are a bit different when you move to the very back of the ship, just below the waterline. That's where the whole idea of a closed hull breaks. Engineers deliberately cut a permanent opening right into the aft end. Running right through that opening is a heavy steel shaft spinning at full speed, transferring torque from the engine out to the propeller. So you've got the sea on one side, your dry engine room on the other, and this spinning rod connecting them. But to stop the ocean from forcing its way in, engineers built a specialized, heavy steel cylinder housing right around that opening. This housing is called the stern tube, or more accurately, the stern tube arrangement, because of everything it encompasses. Back in the day, during the early years of steam, we didn't have any sophisticated means to plug this hole. Do you know what engineers used? Ropes. Yes, early marine engineers would take tight coils of flax rope, soak them in animal fat or tallow, and stuff them into a stuffing box around the spinning shaft. This was called gland packing. It was designed to leak a little bit because the seawater was the major thing keeping the ropes from overheating due to friction. The back of an old ship was a constant dripping mess, and some of the crewmen's entire job was just tightening the bolts on that packing to keep the water at bay. But as ships grew larger and engines became more powerful, greasy ropes weren't going to be effective in sealing against the seawater ingress. And as time went on, ships moved towards proper stern tube arrangements with sealing systems and dedicated bearings. Now, let's unpack this setup. If you take a modern ship into a dry dock and pull that huge propeller right off the end, what you'll be looking at is a bare cylindrical steel shaft. Let that shaft spin against the salt water, sand, and grit, and it would be shredded after a while. To fix this, during manufacturing, builders heat up a thick chrome steel sleeve until it expands, slide it over the shaft, and let it cool until it grips the steel tightly. That liner sleeve is polished to a mirror finish, because it's the exact surface the modern seals in the stern tube are going to ride against. The seals are located at both ends of the tube, but the ones positioned aft, facing the open sea, are the primary line of defense against seawater ingress. These aren't simple rubber gaskets you'd find under a kitchen sink. We're talking about a tight stack of 3 to 5 V-shaped rings made from high-spec elastomers like Viton or nitrile, amongst others. Materials chosen specifically because they can take sustained friction and withstand constant heat without degrading. Now, here's the clever bit. That V-shape is pointed so that the natural pressure of the sea actually squeezes the rubber lip tighter against the spinning shaft. And to make sure it never loses contact when the shaft is vibrating, designers wrap stainless steel coil springs called a garter spring around the back. It acts like a constant tourniquet, keeping the seal perfectly snug around the shaft liner. However, for these seals to work perfectly, the spaces between them need to be filled up with oil. That oil doesn't just get pumped in manually, it relies on a clever bit of basic physics. Up high in the engine room, well above the ship's waterline, engineers mount an oil header tank. By putting the tank up there, gravity creates a natural column of pressure, known as a static head. We want that oil pressure inside the seal chambers to stay just a fraction higher than the seawater pressure pushing in from the outside, usually about 0.2 to 0.3 bar higher. Think of it as a defensive wall. If a seal starts to fail, the physics works in our favor. The oil leaks outward into the sea rather than letting the ocean force its way into our ship. Past the aft seals, the shaft enters the aft bearing. There's a forward one as well, but aft does most of the work. These bearings basically support the shaft and propeller loads. Outside the hull, you have a propeller that can weigh over 70 tons hanging off the end of the spinning shaft. So the bearings have to support that load while the shaft spins at full speed. During manufacture, to ensure the bearings always stay in place, engineers use a shrink fit. They freeze the bearing in liquid nitrogen until it contracts, slide it into the stern tube, and let it expand as it warms up to create a massive, permanent friction lock. The bearing sleeve is made of iron or steel, but the inside facing the shaft is lined with a soft material called white metal, or babbitt. Now, why would engineers put soft metal under a massive, heavy shaft? It's a brilliant sacrificial design. If a tiny piece of hard grit ever manages to sneak past the seals, the soft white metal lets that debris sink right into its surface, burying it so it doesn't scratch or ruin the expensive main shaft. The bearing takes the damage so the shaft doesn't have to. Here's where things get interesting. When the shaft is just sitting idle, it's dead weight, pressing directly onto the bottom of the bearing. Although there's a lot of oil inside this main chamber, there's still metal on metal contact. But the second the shaft starts spinning, the rotation drags oil down into the narrowing gap underneath the shaft. Because oil is thick and sticky, the spinning forces it into a high-pressure wedge. And that wedge is powerful enough to physically lift the 100-ton steel rod right off the bearing's surface. This is called hydrodynamic lubrication. Think about a car hydroplaning on a wet road. At speed, water gets dragged underneath the tire and builds enough pressure to partially separate the rubber from the road's surface. The shaft does something similar, except instead of water, it's surfing on an oil film a few microns thick, riding slightly up and to one side in a normal, lopsided rotation engineers call eccentricity. As long as that oil film holds, there's very little wear in there. But if the oil gets too hot and thins out, or if water leaks in, that wedge instantly collapses. The shaft drops, and the sudden metal-on-metal friction sends temperatures spiking fast. Temperature sensors buried in the bearing wall, called thermocouples, will send alarms straight to the engine control room. Even during maintenance inspections at dock, engineers have to use a specialized tool called a wear-down gauge to measure the exact down-to-the-millimeter drop of the shaft, checking for bearing wear before a crisis hits. Because if the crew doesn't catch it in time and lower the engine load or boost cooling, the bearing completely wipes. This means the soft white metal literally melts and smears across a shaft spinning at around 80 revolutions per minute. And when that happens, the bearing is physically destroyed. And just like that, the ship loses propulsion. You are completely dead in the water. Now, heat, friction aren't the only enemies. The enormous propeller hanging off the end of the shaft acts like a giant lever. It's so heavy that the steel shaft actually bows and droops under its own weight, causing what engineers call deflection. If the bearing hole were perfectly straight, that bent shaft would dig its hard edge right into the corner of the bearing, squeeze out the oil film, and create a localized heat spike. The fix is a technique called slope boring. The bearing hole is cut at a slight angle to match the natural droop of the shaft, so the load spreads out evenly across the surface. Get that angle slightly off, and the shaft starts to vibrate, slamming against the seals until the rubber cracks and turns into a wide-open leak, vulnerable to the sea. Further forward, the shaft travels through the main body or chamber of the stern tube, before passing a forward bearing and hitting the final barrier, the forward sealing arrangement. These seals face the engine room, and their job is dead simple: stop oil from pouring into the ship. But because these seals are inside the hull, they lack the generous heat sink of the surrounding ocean that the aft seals enjoy. To prevent the friction from cooking the elastomer rings and thinning the oil until it loses its viscosity, we wrap that unit with a water cooling jacket, often tied into the ship's central freshwater cooling system. It's a constant thermal battle to keep those rubber lips from hardening and cracking under the heat of a shaft spinning for an extended period of time. At this point, you might be thinking, okay, but we mentioned those other openings below the waterline at the start. The sea chests, the overboard discharges, and the ballast suctions. Why is the stern tube the truly dangerous one? Well, the answer is incredibly simple. For those other openings, you have valves. Let's say a seawater pipe bursts inside the ship. You walk over, close the valve there, and the hole is gone and the ship is safe. You can't do that with a stern tube. You have a massive steel rod spinning in that opening 24 hours a day. There is no valve for a rotating shaft. It is a permanent, dynamic breach in the hull that you can only manage using physics. Because you can't just close it, any small issue can quickly spiral out of hand. To protect the shaft and ceiling from dangerous objects, there is a welded metal shroud around the stern tube opening called a rope guard, often equipped with net cutters, located just ahead of the propeller. But imagine a discarded plastic fishing line manages to bypass that guard. It gets pulled directly into the aft seals. The spinning shaft winds the line into a tight, molten plastic ring right under the seal lips, creating intense friction that destroys the rubber barrier. Suddenly, you're leaking oil into the sea, facing Coast Guard fines that can easily top $40,000 a day while your ship is detained at anchor and bleeding money. But the real trouble happens when the pressure balance flips and the ocean forces its way in. Seawater is an enemy of viscosity. The second it mixes with the oil, it reduces the oil's lubricating performance and film strength, and that high-pressure wedge disappears. As a result of that, your 100-ton shaft isn't surfing anymore. It's grinding on the bearings metal on metal. At 80 RPM, the friction can generate enough heat to destroy the assembly. When there's a stern tube problem out at sea, you either shut down your main engine or risk losing it. Now you have a dead ship. No propulsion power means reduced steering effectiveness. In heavy seas, a ship with no steering turns sideways to the waves and swells. A dangerous situation called broaching. For a container ship, the violent, uncontrolled rolling can cause cargo containers to shift, which can capsize the vessel. That's the direct line from a small seal leak to a total disaster. You might think having a twin-screw ship, 2 engines and 2 shafts, makes you bulletproof. Fair enough, it's a great insurance policy, and you can usually limp home on one, but even then, you aren't out of trouble. A locked, seized shaft on one side creates massive drag, making the ship handle like a shopping cart with a broken wheel. And if that damaged shaft is still vibrating, it can actually cause fatigue cracks in the surrounding hull plates. You're still looking at a repair bill that can be painfully high. If you are stranded hundreds of miles from land, you have to call a salvage tug. And in the maritime world, most salvage tugs don't charge a flat towing fee. They operate under traditional no cure, no pay contracts, meaning the tug company might legally claim a percentage of your entire ship and cargo's value just for saving you. After the ship is salvaged, you face emergency dry docking, waiting for a slot and losing charter profits every single hour your ship sits idle. The stern tube is a constant battle between engineering and the pressure of the ocean. It is the one spot where a system failure doesn't just mean a leak, it can take away the ship's entire ability to move or stay afloat. In 2026, a small percentage of new commercial builds are moving away from oil-lubricated systems entirely, replacing the soft white metal bearings with high-tech polymer bearings and using the ocean itself as the lubricant. Well, this isn't actually new. Back in 1854, the legendary engineer John Penn designed the world's first water-lubricated stern bearings for Brunel's famous megaship, the SS Great Eastern. After decades of increasingly elaborate oil-lubricated systems, the shipping industry is now in a sense, circling back to water lubrication. But the physics of supporting a modern 100-ton propeller shaft on water instead of oil is another story entirely. Thank you for watching this video. Hopefully you've enjoyed and learned something new. I certainly have. If you've enjoyed this, please make sure to like the video, ring that notification bell for more, and subscribe to stay tuned when our latest videos go live. Until next time, thank you for watching.